Good morning, everyone, and welcome to Elevated. My name is Nate Cruz, your moderator, and it gives me great pleasure to host this monthly Elevated Zoom meeting event. Elevated is Caltech CTME's monthly Zoom meeting designed for technology leaders who are passionate about staying informed on industry trends, embracing new ways of working, product innovation, and agility. Our discussions align with the custom courses that we have here in our prestigious Caltech CTME Learning Program. Today, we have a captivating talk lined up for you titled Driving Strategic Innovation, a look at what innovation means at JPL, which will be delivered by one of our incredible instructors here, Dr. Tony Freeman. Dr. Tony Freeman is involved in our custom program. He provides his knowledge and expertise in our custom programs in the area of innovation, leadership, system engineering, and project management. Dr. Freeman is currently retired senior formalization leader at JPL with experience expanding multiple doctorates, and he is a proven track record of success in building programs consisting of many different NASA missions. He has managed concepts of development and successful proposal campaigns for JPL. He has also mentored many of JPL's other senior formalization leaders. As a highly creative individual, he is passionate about what's next in space innovation. Tony has also authored over 300 original research contributions and is still actively publishing his ideas. He is a Life Fellow at the Institute of Electrical Engineering for his work in calibration of synthetic aperture radar systems. Dr. Freeman is a native of Manchester, England. He has a Bachelor's of Science degree in mathematics, a PhD in astrophysics, both from the University of Manchester. Without further delay, I invite Dr. Tony Freeman to the virtual stage. Tony, the floor is yours. We're eager to hear about your insights of innovation at JPL.
Thank you, Nate. Thank you for the great introduction. I'm going to share my screen now and get into the slides. So this is a shorter version of a talk that I gave really on my way out of JPL in April to talk about how we do innovation, reflecting back on my 42-year career, especially the 25 years I spent in formulating new mission concepts. You've seen most of this. My deep technical background is synthetic aperture radar, so that's part of my background there. But I also manage the section on mission architecture and systems, which has about 150 engineers altogether for about 5 years. I led Earth Science formulation. I led our Innovation Foundry, which is where a lot of these ideas sprung from, and then planetary science formulation until I retired in April. So the question that you might ask yourself, which should seem obvious, is JPL an innovative organization? And I think the answer, when you look at missions like Voyager, Galileo, Cassini, the first of their kind missions to the outer solar system, and now interstellar space, Marco, the CubeSats that flew by Mars, the first interplanetary CubeSats. When you look at the Mars rovers, and now more recently the Mars helicopter, Juno, first solar-powered mission to an outer planet, NISAR, the next generation synthetic aperture radar that JPL is working on with the Indian Space Agency, and then finally Kepler, which is a mission that has since ceased operations, but was stared at thousands and thousands of stars in our galaxy to detect the transits of planets across the face of them, which really was our first revelation that roughly half the star systems in our galaxy have planets around them. We didn't know that until Kepler happened. So when you have an organization that undertakes these kinds of missions, robotic space missions, you have to say, yeah, it's innovative. These missions are innovative. They were the first of a kind. They are the first of a kind. And that's the sort of thing JPL prides itself on taking on. So what's the culture of innovation at JPL? How does this all sit with us? What background informs it? And so part of it is decades-long programs. Think about the Mars exploration program, which we've been undertaking now for at least 30 years, within which we have one-off standalone missions, which we call projects. And another key fact is that all work is competed for formally or informally. JPL is not officially a government organization. It's managed by Caltech, and it has to bid either as a proposal or informally in competition with other NASA centers for the work that we undertake. I think most JPLers have a frontier pioneer mentality. We're on the West Coast after all, and that's endemic to California, I think. We have an end-to-end mission capability, so we pride ourselves on being able to do every part of a mission except for the launch. But often we choose not to. So we often partner with industry to provide spacecraft or instrument capabilities or et cetera. And we also partner with international partners too. But knowing how to do it is a key factor in JPL's success. Tremendous creativity from our engineers and scientists. You scratch any JPL engineer or scientist, you'll find 5 ideas for a mission, we like to say. People say about us that we can innovate our way out of any problem. That's what NASA comes to us to do. And so, we're seen as an innovative organization from outside. And the competition that I mentioned earlier, I think we thrive on that. It really keeps us sharp, keeps us trying to be on the cutting edge at all times. The negative side of the culture is a severe not invented here syndrome. It's very difficult to imagine that other people can do great things. They do, of course, but sometimes JPLers have to remember that. And having competed so hard against some of our competition, it's hard to see them as partners sometimes. So that's the downside of that. What does innovation mean at JPL? Well, it means bringing a new idea to market, really. But our market is the science community and their interests. So innovation at JPL means translating an idea or invention into something that creates value for which customers will pay. Customer is NASA, the end customer is the science community, and we think we keep them very happy. I note that it's not the same as creativity. That's a mental characteristics that allows people to think outside the box. And it can result in innovative or different approaches to a particular task, but it's not innovation at JPL until and unless it flies. So infuse a new technology, have a great idea for a mission, infuse a new technology, but until it flies, it's not really innovation. I'm a big fan of Professor Zoe Sandfarber, George Washington University in DC. She's done a lot of work that's based on her deep experience with NASA. She's embedded at Goddard Space Flight Center. She visited us on many, many occasions when I was the head of the Innovation Foundry. And she's put together, what she thinks innovation within a NASA context is all about. And it's these S curves that you see here they show technical performance increasing over time, but it's a nonlinear increase. So it starts to go slowly at first, then it accelerates, and then for a given technology, it tends to saturate. It's hard to get a new return, a good return for your investment until you jump to a new S curve, and then you get on that steep slope of the S curve again. So this is termed exploitation, moving up a particular S curve. and exploration jumping to a new S-curve. And if you put enough of those together, you can see you get an exponential growth curve like this. So if you stack S-curves together, it sort of looks like you have exponential growth. This is the Moore's law example where you have transistors and their throughput rate as a function of time. But this wasn't a constant type of technology. The materials changed, the procedures changed, the etching processes changed over time to get to where we are today. It's not a new construct. So I found this dated back to the 50s, may even been earlier, but this is the earliest I could find, from a 1953 report by the US Air Force, where they were looking at methods of propulsion as on the performance side, they had the fraction of the speed of light that you could execute with that. They started off looking backwards, and they said, well, the Pony Express could go at only a very, very small fraction of the speed of light. And then we have trains and autos, and then we get into the propeller-driven aircraft, jet-driven aircraft, missiles, gas turbines, chemical rockets, and then they projected forward to nuclear rockets and what they would be capable of. So this was a way of thinking for the Air Force long-term to see what technologies they should be investing in to determine what their long-term investment budget should be, near-term, and mid-term. So in the JPL context, exploitation and exploration. Exploitation allows us to move up a particular S-curve, initially with a slow start, followed by a rapid improvement in capability, then a plateau effect. Explorations jumping to a new S-curve. That means we transition to the next one with a new technology. And again, this is reference to one of Professor Sanfarber's excellent papers. In exploration at JPL, we jump into a new S-curve, applies really well to one-off space ventures, like a space mission. And if you think about big space missions in astrophysics or in earth science or in planetary, the opportunities occur on decadal timescales. We always strive for the next generation in performance in these missions. And as Professor Sanfarber says, in the current paradigm of a few flagship missions separated in time by decades, the directed one-off push for performance is not obviously inefficient. I can translate that in baseball parlance as, in other words, you may as well swing for the fences when you do one of these missions. And in a JPL context, our lab motto is dare mighty things. So that fits very well with this paradigm. I want to talk a little bit about disruptive innovation. That's where you have something that starts off initially at the bottom end of the market and then relentlessly moves up and takes it over. And I'm going to show you an example of how JPL responded to the innovation of CubeSats. I'm going to talk about how we responded there. And there are 5 basic types of responses. You can carry on and invest in your traditional business. You can ignore the innovation. It's not your business. You can attack back by disrupting the disruption, come up with something else that destroys it. Or you can adopt the innovation by playing both games at once. That's the way we chose to do it. Or you can embrace it completely and scale it up. We decided not to do that, but we adopted number 4. This innovation process model I find interesting. It shows how innovations start off at the left in the green circle, and they can either be an architectural insight, think landing on Mars with a sky crane, or a technology insight, a new type of detector enables a new measurement. And in either case, you explore the the implications of that technology or that architecture by executing studies that insert the technology or the new architecture into a mission. So architectural studies, I've done many of them. We did lots of them in Innovation Foundry with our Team X. And they often are designed to identify gaps in technologies that we will need for the future. And then they go down to the technology exploration box. Once you've demonstrated those technologies, you have advanced the technology readiness level or the TRL, you can start to include them in your mission studies. That's the architectural exploration, and put them in a demo mission. If you think of something like the solar panels on Deep Space One, that would be a demo mission that allows you to do that. Going into the exploitation box, that would be a mission that applies this for science, and then moves it forward so that it's then in our flight catalog for the future. So solar panels went from a technical demo with Deep Space One to a science mission demo with the Dawn mission. And then ever after that, we've used solar panels and solar electric propulsion for many missions. There's other arrows too. Sometimes you leap from technology exploration, looking at helicopters that might fly on Mars, to an opportunity to go directly to flight without doing the detailed studies. We did that with a Mars Ingenuity helicopter. Sometimes, though, the technology fails or it gets delayed. And so when that happens, you end up in Professor Sandfarber's model in a treading water environment where the technology just takes a long, long time to get to market, and doesn't really make it until there's an opportunity that fits that technology, and then you get to go fly it. But sometimes from the treading water stage, you go to attrition, and then it's a death knell. You go to the graveyard, and the technology dies on the vine, as we often say. So sometimes when technologies go to the grave, it's because we learned the wrong lessons from failure. So when a new approach fails, we, JPL, as I'm sure other organizations are prone to too, we sometimes draw the wrong conclusions. The famous failure of the Galileo antennas to deploy en route to Jupiter was fixed by essentially employing JPEG compression to get the data down at lower rates. But the conclusion drawn by generations of JPL engineers and managers was that deployable antennas were bad, and so no deployable antennas were flown on a JPL mission for a couple of decades afterwards. Similarly, the failure of the Deep Space Two impactors put a cloud on penetrator missions, so we haven't flown any penetrator missions since then. And I think it's quite likely that the failures of the Artemis 1 CubeSats, which were not the fault of the CubeSats, is already leading to comments like, well, deep space CubeSats are just toys from senior managers. And so that I think that's going to make it hard to get a CubeSat mission flown again in the future. So S-curves, I said we look at some S-curves. So they represent an advancing capability over time with a slow start where the technology is just coming on stream, an upswing where you're very rapidly making progress to a point where you have diminishing returns. And even though you're improving the technology, it's harder to see an improved output in terms of science for us, or maybe profit if you were a profit-driven organization. In my own background, as I said, I'm synthetic aperture radar is my deep technical background. When I got to JPL, they'd had the SIR-A shuttle radar, SIR-B, and CSAT missions, which laid the groundwork, foundations for synthetic aperture radar, but didn't really take off. They weren't long-term observations. The science community weren't using that data. It was an interesting technical exercise. They shook out a lot of the bugs, but it didn't really get a lot of traction from the science community until we flew the AirSAR, our airborne SAR system, where we had 3 different frequencies. We had all kinds of polarizations. We had all kinds of interferometry with antennas at the front of the plane, at the back of the plane, on the side of the plane. It was all over the place, making every possible kind of measurements that synthetic aperture radars are possible to do. And then we put a lot of that into the Circe XR shuttle mission, which had 31 different modes of operation. And then we progressed that to the UAV SAR, which was the first exploration of autonomy and flying very accurate repeat tracks. And then finally, the shuttle radar topography mission, which was a purely interferometric SAR mission. Interferometric SAR allows you to produce a digital elevation model. And SRTM's digital elevation model is still the gold standard for digital elevation models today. So the technologies we infused in these missions are calibration. The AirSAR was the first calibrated data anyone had ever seen from a synthetic aperture radar. Polarization diversity, we call polarimetry. Interferometry, using 2 antennas. And phased array antennas, which was on the Circe XR and UAV SAR missions, and SRTM. But as you sort of see here, I've indicated that as we got to the top of the S-curve with SRTM, it became very difficult to imagine what was the next thing that we would do that would differentiate us from our competition. JPL follows a differentiation strategy, primarily, that we try to be one better than the competition in general. And it was hard to imagine what missions would allow us to jump to the next S-curve in synthetic aperture radar. So we did solve that problem. We applied a bunch of different techniques to the UAV SAR. We added some different frequencies. We tried some different processing techniques. And that resulted in a slew of missions, one of which is an ESA mission, biomass, but it comes out of the JPL architectural exploration that we did. The SMAP mission, which as you see has a deployable reflector antenna, that was a synthetic aperture radar to measure soil moisture. The SWAT mission, which is an interferometric altimeter that's now measuring ocean altimetry to unprecedented precision, to the Veritas mission, which is currently in the works to go to Venus and produce the same class of DEM at Venus as was done with the SRTM mission, using different updated technology. And then finally, NISAR, which is the culmination of a series of innovations in synthetic aperture radar, including the reflector antenna, including a phased array feed, and including the phased array antenna and the feed, but also the sweep SAR technique, which I came up with, and I named after our lovely golden doodle Sweep, who passed away a few years ago. So the technology is infused deployable reflector antennas, interferometric altimetry, reflector array antennas on the SWAT mission, onboard processing on Veritas to knock the data rate down back from Venus by a factor of 10,000, and then finally sweep SAR. Mars surface exploration also followed an S-curve. They jumped to a new capability with the Pathfinder mission and the Sojourner rover back in 97, 98. And from that stemmed the 2 MER rovers, Spirit and Opportunity, first solar-powered rovers on Mars. They explored large areas of their landing site. And then new landed missions like InSight, which carried a seismometer, state-of-the-art seismometer, and recently discovered water on the surface underneath Mars, deep underneath. The Phoenix mission, which discovered water also in the polar regions just below the surface. And then the RTG-powered rovers, Curiosity and Perseverance, that carry very sophisticated instrument suites. Curiosity targeted at geology, and Perseverance targeted at organics, organic chemistry, and sample collection. And then finally, we have the helicopter, which has served as a scout, but has also demonstrated a new capability for Mars exploration. All of this culminates in the Mars sample return, which is an extraordinarily complex and difficult mission. And the science community are struggling greatly with how to do that mission, but also what comes after it. That's why I show it at the top of the S-curve. It's very difficult to do, very difficult to improve on, and very difficult to see what the next S-curve looks like in that particular arena. Technologies infused include solar-powered rovers, airbags for landing with the Sojourner mission, Pathfinder, MMRTGs, that's radioisotope thermal generators that can operate in an atmosphere, in situ instruments made leaps and bounds with Perseverance and Curiosity, autonomy with the helicopter, and then the Sky Crane deployment system, which landed Curiosity and Perseverance. So I said we'd look at CubeSats. JPL's history with CubeSats goes back quite a long time, to the early 2000s with the MEPC missions that were released off one of the space shuttle flights. And then we didn't do much with CubeSats for quite a while until the Asteria mission in 2016, I think it was. And the reason for that was that CubeSat technology, in terms of the flight system, avionics, communications, power generation, etc., really developed slowly between the early 2000s and about 2012. But in 2012, we could see that CubeSats were, ready to fly complicated measurements, complicated instruments. So Asteria is a mission that does a one star at a time Kepler. It stares at a star, it looks for a transit of a planet. And it did actually detect planets that we did not know about during its mission. Then we had Tempest D, which is another CubeSat for Earth science with a microwave radiometer on it that can measure profiles of hurricanes. RainCube, first radar flown on a CubeSat with a deployable reflector antenna that came out of a soup can size dimension. HITE, a thermal imager. A signals of opportunity mission called Snoopy that measures reflected signals from a UHF Navy satellite. Pre-Fire, which has a far infrared spectrometer to measure a key aspect of the climate budget, the Earth's energy budget. And then finally, Sunrise, which is a swarm of CubeSats that each has a HF, a radio receiver, an antenna to resolve coronal mass ejections from the sun. So this is a very, very high value science that will allow Sunrise to monitor coronal mass ejections and how they develop, to understand how they re-engage back with the sun and recirculate over time. So that's really cool science. I've shown it at the top of the S-curve because I know it's hard for our scientists and engineers to think, what do we do to top Sunrise? This is decadal survey class, National Academy of Sciences science done by a CubeSat mission and hard to top. I showed improving performance, but I wanted to share with you what we saw happening in the evolution of CubeSats over about a 10-year period from 2012 to 2022. So when we began thinking about CubeSat missions, the typical downlink rate from a CubeSat with UHF or VHF was about 1,200 bits per second. So from low Earth orbit, the fastest you could get data back was 1,200 bits per second. That's AOL dial-up kind of rates. Then a commercial company put an S-band system on a CubeSat, and the data rate leapt to 2.4 megabits per second. We put a Iris radio on a CubeSat called ISARA in 2017. We coated the back plane of a solar panel with a reflector ray antenna and used that as the primary antenna. And we demonstrated that you could get 100 megabits per second back from that using that technology. And then finally, optical comm came in, and the Aerospace Corporation demonstrated 200 megabits per second downlink rate. I think they actually exceeded that before the end of mission. And then T-Bird, which was MIT Lincoln Labs, demonstrated laser comm at 200 gigabits per second in 22 with the T-Bird mission. So that's an increase by 8 orders of magnitude in 10 years. It's pretty impressive. And we saw that in other areas too, in terms of power generation, in terms of instrument capability, in terms of pointing accuracy, and all the things that you want spacecraft to be able to do. CubeSats demonstrated that they could do with the same kind of performance increase. We also got into planetary CubeSats and small sats. So Inspire was the first one of these. It never flew, but it was designed to fly past the moon and relay camera measurements, magnetometer measurements back. And the team that worked Inspire solved all the problems of how you communicate back to Earth from a CubeSat, how you navigate, how you orient yourself, how you generate power, how you keep the temperature stable, etc. And we took it through thermal vac and solved all of those problems. But we could never find a ride. So we could never find a rocket that would send us in the right direction. But the effort wasn't wasted. We quickly infused it into Mako, the two interplanetary CubeSats that flew with InSight. They launched on the same rocket and then navigated their way independently to Mars, and then relayed the InSight landing data, which was out of sight of direct sight of Earth. They relayed that landing data back to Earth at a data rate of about 8 kilobits per second, which was just enough. That's what they needed to get back to see that the telemetry was there, but also to indicate back to Earth that InSight had landed successfully, and when Mars rotated around again, they'd be able to see and receive data from the mission. I had a couple of failures along the way. We had the Near-Earth Asteroid Scout, a solar sail mission to fly past an asteroid and give us spectroscopy data. Lunar Flashlight, which would have penetrated the permanently shadowed regions, craters at the lunar poles, to get reflections from ice crystals. But both of those missions, as I mentioned earlier, were on the Artemis 1 launch. They were unfortunately kept on the launch vehicle for 18 months. Those of you that are in the spacecraft business know that you don't put a spacecraft on a launch vehicle in Florida in that humidity and expect a positive result. So that's kind of what happened there. But the technologies were all proven on the ground, and the Lunar Flashlight actually worked in space, but it didn't go through its entire mission. But others went on to do great things. BGQ DART mission flew in a CubeSat dispenser and was deployed within a couple of days of arrival at the Didymon asteroids. And it observed the DART impact and relayed pictures of that back to Earth, demonstrating that CubeSats can operate independently in deep space as ride-along missions with a mothership. We're pursuing the Lunar Trailblazer mission. I think it will launch within the next year. It's a small sat, not a CubeSat. It uses a lot of the same approaches. Our partners, Lockheed Martin, have embedded those. It's got a miniaturized spectrometer on it, imaging spectrometer, a miniaturized thermal imager on it. And it's going to look for water ice and water and gas and liquid phases on the moon. And then finally, we have Droid, which is our probably most ambitious CubeSat smallsat mission to go rendezvous with the Apophis asteroid that will fly by Earth in very close in 2029. Rendezvous before that happens, and with a pair of CubeSats deployed, like the DART mission, observe with an HF radar the changes on the surface and within the structure of the asteroid, so that we can understand how objects like that change over time, especially when they get into a gravity well, like the close flyby of Earth. The technologies infused there include the Iris radio I mentioned earlier, reflector array antennas on Marco, solar sail on NeoScout, compact lasers, compact instruments like hyperspectral and TIR, and then the HF radar. So how did we do that? How did JPL get involved with CubeSats? I'm also going to address why, but how? How did that happen? Well, a bunch of us could see that CubeSats were starting to be capable enough to allow us to do some things with CubeSats that we wanted to do with science missions, but couldn't do because they take so long. I mentioned the decadal timeframes. Those are great, but if you miss the start of that mission, that means you have to wait another decade. CubeSats allowed us the chance to infuse things much more quickly. So we formed a group that included formulation office managers in earth science, planetary and astrophysics, engineering organization representatives who were interested in this new technology, deep space network leaders, technology leaders, and then we engaged our Innovation Foundry to allow us to explore architectural solutions rapidly. And all the people that I listed here had the ability to direct resources from the laboratory's front-end investment budget. So we were able to steer things towards being able to do CubeSat formulation, CubeSat implementation, and operations. We had some high-level champions that gave us cover and also support and encouragement. They included the laboratory director, that's probably a must, Dr. Alachi, but also we had great support from the associate director, Farouz Naderi, and that was followed by associate director Jacob Van Zyl. Both of those people gave us wonderful support as we moved along over about a decade. So what did we do? Well, the tactical approach was to create and win opportunities for CubeSat missions. So if there wasn't an opportunity, we would steer internal investment towards flying our own CubeSat. If there was an opportunity, we would do our best to try to win it. And fortunately, NASA, in this time period, 2012 to 2022, created a lot of CubeSat mission opportunities that we were lucky enough to win several of. We also trained workforce in how to build and think about CubeSats. We invested in facilities that were tailored towards integration and test of those kind of spacecraft. We developed telecom solutions for deep space CubeSats. This was not an easy problem to solve, but we did. We invested in reduced size, weight, and power instruments and key subsystems. So some things like Iris radio, we had to just invent ourselves. We also invented antennas that we could use to communicate with deep space CubeSats. And our earth science and astrophysics folks really wanted instruments that could fit in a CubeSat form factor. So we developed those initially on our own dime, and then with NASA funding to support that. And then last but maybe not least, we put together a flavor of TeamX that we called TeamXC that would allow us to do fast, implementable, architecture and design studies. My mandate to the team to put this together was the study should not cost more than the typical university CubeSat. So we had to bring the cost way down. But those studies were actually quite accurate, that they often predicted the configuration very precisely, the mass of this CubeSat very precisely, and the overall performance. So what came out of a Team XC study was very like what the team that we're going to build would build. So for Marco, for example, that allowed them to build the Marco CubeSat in, I think it was 15 months altogether. So we used, industry developed stuff. We developed some of our own things, but we knew their size and weight really well, that we could stack them together and then go build that. At the top level, the strategy was be first to market. That's always a JPL desire. And we wanted to be the first ones to fly interplanetary CubeSats, for example, or make high quality science measurements from CubeSat platforms. We also wanted to reduce the size, weight, and power of our instruments and other things, other subsystems, to feed forward into more mainstream JPL missions. And that happened to a degree. If you build a smaller instrument, it can more easily fit on a larger spacecraft. So that allows you to do that. We also wanted to advance our software capabilities, which we did on Ingenuity, for example, but also on Lunar Flashlight, to feed forward, again, into more mainstream JPL missions. So takeaways. If you're truly innovating, I think I indicated it's okay to have a few failures along the way. That's going to happen. It is much easier to be innovative when you find yourself on the upswing part of an S-curve. As someone who's been in that situation a few times in my career, it was great fun. When we were on the upswing, you're doing things that no one's ever done before. Everyone wants to come and work with you and learn how to do it. You can go to conferences and, win prize papers, all that kind of stuff. It's great. So look for opportunities to get your organization on the upswing, whatever business you're in. And then if you find yourself at the top of one S-curve, don't worry. You might have to think really, really hard about it, but there is always another S-curve that you can jump to. So it's just finding the right one and making the investments at the right time that allow you to make that transition. And I think there I can stop talking and take some questions.
Okay, Tony, thank you for an amazing presentation here. I appreciate it. You showed all the knowledge that you've generated. You showed all the innovation activities that go on at JPL. You also showed the successes and the failures and how you can leverage both of them in your roadmap and cycle to continually develop the organization, to which I thank you. So folks, this is your opportunity to ask questions. And we have Stacy here is going to be my assistant who will be monitoring the chat for different questions. But I'm going to start out with a few lead questions to get things going. So Tony, one of our goals here at Elevated is to get people engaged to come and see you in some of your class activities. So taking one representative one, AeroPM, could you kind of tell us what kind of things you do in the AeroPM program to add value and knowledge to the students that are in those programs?
Yeah, that's great. I think I told Mike the class that I really like teaching is the cost and schedule one, the costing and scheduling, because I have some experience in that, and I always love reviewing that, because fitting the cost and schedule to the scope of what you're trying to do is always extremely difficult in the business we're in, and it also requires innovation. Sometimes I love the introduction in the AeroPM class of risk and opportunity management, for example. That's the idea of opportunity management, something that came in the last decade or so, and instead of having to carry budget for all your risks, it allows you to generate surplus resources through proper management of opportunities to save time, save money, increase scope where possible. So those are the kind of things that I like to inject. Innovative ways of thinking about problems we all face.
Okay, thank you, Tony. I think that gives everybody a great insight in to be able to choose and pick to join an AeroPM class and get a more comprehensive description of what you provide. So thank you very much. I have a few other questions here to ask, and folks in the session here, please put in chat any other questions that you'd like to have here. So, Tony, you had mentioned where JPL has adoption of a differentiation strategy. Where did that stem from? Could you give us the history of that, please?
Differentiation strategy, I think, comes from the parent organization. So Caltech is it's a very small university that's about, I would say 10 times smaller than MIT, but they're very competitive with MIT. And they try to do that by having professors and research activities that are kind of on their own. They're off on a frontier, decoding the human genome, coming up with CMOS detectors. That's the kind of thing Caltech likes to do and pride itself on. And I think we're managed by Caltech, and it's a light management, but I think that culture flows into the organization.
Okay, so what I'm going to do is interject. We had a question here that I see in the Q&A here. How do you weigh the risk versus benefit of jumping into a new S-curve, and how do you project and estimate the time to do it?
Yeah, it's a great question. JPL has many avenues of business, and sometimes I think in the example I gave about the radar and the CubeSats, it's quite likely if we don't jump to a new S-curve, we will go out of that avenue of business. Mm-hmm. So it's almost a binary decision forced on you. You either do it, you either jump to the new technology, or you decide that I'm not going to be, as an institute, in this line of business, and we can do something else, pick another line of business. So those have been the situations I've been in. Jump into a new technology when it's not quite so stark. Yeah, that's a great question. If it saves you money, if it allows you to do more scope, better science return. Typically, we haven't used schedule as a driver. That's been, we all hope that our missions can be done on time, and we try to allow enough time to do the technology development. And we always try to allow a backup in case the technology doesn't mature. But we've largely allowed scope and cost to drive those decisions.
Yeah. Thank you very much. And thank you from the audience for adding that one question in here. The next one, Tony, you talked about the U.S. Air Force S-curve on rocket propulsions. And that's a really interesting question to ask here. Can you go and elaborate on that a bit here to give the audience a little bit more context, please?
I can, yeah. So you saw it was done in the 50s. So they had, this was the Wernher von Braun era of NASA. They had kind of chemical rockets. They hadn't been up into space yet. But, they could see what was coming in the future. And they had chemical rockets. They had a projection of nuclear rockets. And nuclear rockets have not materialized. But you can also see that they said we'll have interplanetary spacecraft enabled by nuclear rockets. So the nuclear rockets didn't happen, but we still have interplanetary spacecraft. Voyager has gone into, interstellar spacecraft. Voyager has gone into the interstellar medium. It passed out of the solar system a few years ago. So how did that happen? it happened because JPL engineers came up with the gravity assist technique.
Mm-hmm.
So you would accelerate your spacecraft using a flyby of Jupiter, then Saturn, then Uranus, then Neptune, and you'd build up enough speed that within a lifetime of the mission, or even beyond the reasonable lifetime, you could get into the interstellar medium and make measurements. The nuclear propulsion, though, is actually coming closer. There's a couple of DARPA-funded, NASA-supported missions in the next decade. One's called Draco. That's a nuclear thermal propulsion system. One's called Jetson. That's a nuclear electric propulsion system. They're both led by Lockheed Martin. And I've led a study recently that looked at what you could do with that technology. And it's going to be very powerful when it happens. The ability to get to the outer solar system and back again, we'll be able to do that significantly faster than we can now. So the goal for the science community would be to bring back samples from, say, Pluto or from a Kuiper Belt object. And those things now seem to be within reach. I'm not saying I'll live to see them, but within a few decades, we can expect to see that kind of mission materialize.
Okay,
So
thank you for a fairly comprehensive and very informative answer to that question. We got another question from the audience here, Tony. I'm going to throw this one on you. How do you manage it when you have multiple technology options in a line of business? Essentially, prioritizing the scope of what is essential or needed as possible here. So how would you address that question?
That is a great question. So we had multiple technologies for CubeSats, multiple technologies in the radar world. I think that in the radar world, I know we prioritize things based on what provided the biggest science return for the buck. Mm-hmm. So that was definitely the sieve that we used. Okay, does this particular technique, this particular technology provide the best science return for the dollar? And that actually moved us away from, for example, phased array radars. They were so heavy and massive and costly to put up in space that we went towards the reflector antenna and a phased array feed, because that technology was much less mass extensive, and much less costly than a full up phased array.
Okay. Well, thank you for that great question on that one. And thank you again from the audience here. And if you have any others, we would welcome them as we start to close out the session here. Tony, I have one more question, if I may, on this. The topic here is, did you meet resistance in an area, and specifically as you're adopting the disruptive innovation of CubeSat at JPL? What kind of resistance? Is it cultural? Was it technology? Was it cost? What kind of resistance may you have faced as you try to evolve in that new innovation space?
Yeah, so we met resistance every step of the way. So remember the not invented here aspect of our culture. So it was really hard because it came as an outside innovation that we were adopting to try and do JPL missions. So we got comments, CubeSats are toys. If you work on CubeSats, it'll kill your career. They'll never be able to do science. And just, we were able to prove them wrong. You could never get the data back. We proved everyone wrong at every step of the way. There are still some naysayers, but we met resistance. I mentioned the top cover we got from the very senior leadership of the lab. That was really helpful. Okay. It allowed us to just get on and just do it and show everyone that their preconceptions were just wrong.
Good. It sounds like executive sponsor support and great communication kind of helps you to get past those obstacles.
Yeah. I think it's very similar to the lacrosse mission. L-Cross mission, I'm sorry, that Northrop Grumman did. They had top cover from their senior leadership that sort of got a lot of the institution's bureaucracy out of the way, and a lot of the naysayers out of the way, and that really helped.
Okay. Well, Tony, this has been a wonderful experience, and thank you very much. I know you and I have crossed paths back and forth as we try to teach some of these in courses, particularly AirPM, and haven't had an intimate session like this, but I really enjoyed this. I think you gave us an amazing session here today. Everybody else in our session here, thank you for participating. This has been one of our monthly sessions talking about new innovation areas. We'll be continually bringing you our amazing, prestigious instructional staff to come in and talk about new ways of doing technologies and new ways of doing things. Thank you very much for your time and attention today. And I look forward to you to come forward in our next session here coming up in October, talking about another area of innovation. Until then, be elevated.